So, if you ask a large language model to write a really complex, highly specific Python function, it looks like an absolute genius.
Oh, totally. Like magic.
Yeah, exactly. But if you ask that same model to just build a simple, like 3-page web app from scratch, it completely loses its mind.
It really does. It hallucinates. It forgets the database structure halfway through.
And you usually end up with this broken generic script that you have to rewrite yourself anyway.
Pretty much every time.
Right. And why is that? It's because we treat these models like supercomputers, when in reality, to get them to actually build software autonomously, we need to treat them more like junior project managers.
That's a really good way to put it.
Welcome to the Deep Dive. Tonight we are speaking directly to you, the software engineer, sitting there in dark mode at 2 a.m., trying to bridge that massive gap between just prompting an LLM and actually architecting a functional, autonomous AI agent.
It's a huge gap.
It is. So today we're digging into the mechanics of what's called task decomposition. We're figuring out how these agents actually plan, how they execute, and how they survive the really messy reality of code generation.
Yeah, because moving from a standard, text production engine to a true agentic system, it requires this fundamental shift in architecture.
Right, you're not just asking for an answer anymore.
Exactly.
Yeah.
You are spinning up a continuous loop: reasoning, action, observation. And to make that leap, the absolute core capability you have to engineer is task decomposition.
Breaking it down.
Right. An agent has to take a massive, ambiguous goal and just shatter it into manageable, executable pieces.
Let's ground this in reality for a second because, every developer knows the pain of dealing with monolithic requests.
Oh, the vague JIRA tickets.
Yes. If you're in a sprint planning meeting and someone drops a ticket that just says, build the entire user authentication system, you can't act on that. It's paralyzing.
Right, because there's 100 hidden steps in there.
Yeah.
Exactly. Database schema design, setting up the API endpoints, token validation, password hashing. It's a lot. To get anywhere, you have to break it down.
You have to.
But the trap here, and I think this is where a lot of agent architectures fail right out of the gate, is figuring out exactly how small those pieces should actually be. You have to find this incredibly narrow, Goldilocks zone of granularity.
Yeah, granularity is the foundation of the entire system. If you get that base unit of work wrong, your execution engine is doomed before it even makes a single API call.
Wow, really? Before one call?
Yeah, because think about it. If you configure your agent to tackle subtasks that are too coarse, like configure the backend, the model just faces this overwhelming decision space.
Too many paths to choose from.
Exactly. Its attention mechanism gets diluted across way too many possibilities. It doesn't know whether to start with the server setup or the database routing, so it just begins guessing.
And we know how that ends.
Right. Those guesses compound into hallucinations, and suddenly your agent is importing libraries that don't even exist. Right, but on the flip side, though, I've seen developers try to overcorrect for that.
Oh, the micromanager.
Yeah. They try to force the agent to plan out every single keystroke. Like they want a subtask to be write line 10 of the authentication controller using a const declaration.
Which is just absurdly fine.
It's way too fine.
And it causes a complete system collapse, just in a different way.
How so?
Well, when you force an LLM to operate at that microscopic level of granularity, the plan becomes incredibly brittle. And more importantly, you blow out the context window with trivial noise.
Right. It loses the big picture.
Exactly. It loses sight of the overarching goal, which is building the auth system, because its limited cognitive load is entirely consumed by, obsessing over the syntax of a minor helper function.
So finding that sweet spot is tough.
Very. Defining subtasks that are independent enough to be executed without ambiguity, but substantial enough to represent actual architectural progress, that is the first major engineering hurdle.
Wait, let me just challenge that for a second, though.
Sure.
If the overarching goal is autonomous execution, why don't we just dump the entire code base into the context window at every single step?
You could.
Like let the model see the whole forest and the trees simultaneously, right?
Yeah.
So it can reevaluate on the fly. Because models have massive context windows now. 2 million tokens, sometimes more.
You could totally do that, but you'd rack up a $50 API bill in about 10 minutes.
Okay, fair point.
And your latency would be catastrophic. But honestly, more importantly, massive context windows do not equal massive reasoning capabilities.
Right, they still lose track of things.
Yeah, even with a 2 million token window, a model suffers from lost in the middle syndrome. If you bury the immediate subtask inside a mountain of irrelevant boilerplate code, the model's attention weighting gets really fuzzy.
So you have to isolate the reasoning environment.
Exactly. The agent should really only see the specific files and state variables it needs to execute the current subtask, nothing else.
Okay, so let's say you nail the granularity. You constrain the context, and you force the LLM to spit out, say, 20 perfectly sized subtasks.
Okay.
You think the hard part is over.
Yeah.
But if you just feed those subtasks back to the LLM one by one, the whole system still collapses.
Yeah.
Because having a list of tasks is not the same thing as having an actual strategy. So once we have the chunks, how does the agent actually tackle them?
Well, the current architectural consensus kind of splits into two distinct execution paradigms. You've got the plan then execute model and the interleaved planning model.
Let's start with plan then execute.
Right, so the plan then execute approach is very traditional, very top-down. The agent's orchestrator looks at the main goal, generates a comprehensive chronological master plan of all the subtasks up front, and then it just steps through that list blindly from start to finish.
And to be fair, it yields a highly coherent, optimized plan. If you log it out of the console, it looks brilliant.
It really does.
It feels like you've built an AI architect.
It looks brilliant, right up until the exact moment it makes contact with reality.
Right, because things break.
The vulnerability of plan then execute is extreme brittleness. Say step 3 is download and install the authentication library, but the package manager times out or the library's been deprecated.
The agent doesn't care.
No, it doesn't pause to reconsider. It just blindly proceeds to step 4, attempting to call functions from a library that was literally never installed.
So the entire cascade fails, but the agent just keeps looping through the remaining steps, hallucinating code for a broken environment.
Exactly. It's a mess.
Which obviously pushes a lot of engineers toward that second paradigm, interleaved planning.
Right.
This is where the agent adapts in real time.
Right.
It plans step 1, executes it, observes the result, and then decides what step 2 should be based on that new state.
That's the theory, yeah.
But looking at how this actually behaves in production, I mean, isn't interleaved planning just a highly academic term for winging it?
I mean, yes, it is entirely improvisational. The agent is essentially just reacting to its immediate environment without a cohesive master strategy.
So it solves the brittleness problem.
It does, because the agent can pivot if a package fails to install. But it introduces a new, arguably more dangerous risk, which is hitting local optima.
Let's translate local optima into a specific coding nightmare for the listeners.
Okay, go for it.
Interleaved planning is like an agent realizing that a specific data parsing function is running a bit slow, right?
Sure.
So reacting to that immediate problem, it decides to rewrite that entire function in Rust to optimize the speed.
Which sounds great on paper.
Right. In the moment, looking only at that one step, it feels like a massive win. But because it's improvising and it lacks a global view of the architecture, it doesn't realize the rest of the CI/CD pipeline is configured strictly for Python.
Oh, no.
Yeah, the agent just completely broke the build pipeline because it couldn't see the forest for the trees.
That is a textbook local optimum. The agent maximized the efficiency of a single node at the catastrophic expense of the entire system.
It walked itself into a dead end.
Because it was navigating a maze with a flashlight that only illuminated like 1 foot in front of it. So you have this fundamental tension.
A rigid master plan that shatters on impact with real-world friction.
Versus a hyper-reactive improviser that totally loses the overarching architectural vision.
This means we have to accept a pretty harsh reality when building these systems, which is that failure is not just an edge case.
No, failure is guaranteed.
Right. The rigid plan is going to hit an unexpected error, or the improviser is going to break the build. The agent is eventually going to hit a wall, which means the most critical component of your system is the ability to replan.
Yeah, and replanning is where the engineering complexity just spikes dramatically.
Because it has to fix its own mess.
Exactly. It's not enough for an agent to generate code. It has to survive its own mistakes. To successfully replan, the architecture requires 3 distinct operations.
Okay, what are they?
First, it has to accurately detect that its current plan has been invalidated. Second, it has to construct a new pathway based on the failure state. And third, and this is key, it has to preserve its completed work, rather than just wiping the slate clean and starting from scratch.
Let's zoom in on that first point, detecting failure. Because as developers, we take this for granted.
Oh, totally.
If a build fails, We get a stack trace. We get a bright red terminal output telling us exactly which line threw the exception. But an LLM is essentially just a text prediction engine sitting in a vacuum.
Right.
How does it actually know when its plan is officially dead? Do we just, like, parse the standard output and do a string match for the word error?
No, string matching is way too fragile. For an agent to detect invalidation, you actually have to build an evaluation layer around it. The LLM has to transition from a text generator to a state observer.
Okay, so it watches what happens.
Right. When the agent's execution engine runs a Python script, it captures the standard output and the standard error. But it doesn't just read it. It has to evaluate it semantically.
But how do you enforce that structurally? Because, I mean, if you just feed a raw error log back into the main prompt, the model often just apologizes and hallucinates a fix that doesn't actually work.
Oh yeah, the infinite apology loop. I apologize for the confusion. Here is the corrected code, and it's still broken.
Exactly. It gets stuck. So how do you stop that?
You introduce an adversarial setup. You pipe that Strutter output not back into the main agent, but into a secondary critic prompt.
Oh, critic.
Yeah, and the critic's entire system instruction is to be deeply skeptical. You force the critic model to compare the expected state of the execution environment against the actual state.
So it's checking the work.
Exactly. Did the script return an HTTP 200 or 404? Did the database schema actually update, or did it throw a foreign key constraint violation? If the delta between the expected state and the actual state is too large, the critic flags the step as invalid and it just halts the execution loop.
Okay, so that prevents the infinite apology loop. The critic forces a hard stop. But I feel like that leads right into the most painful part of replanning, which is state preservation.
State preservation is huge.
Because every developer knows the sheer, unadulterated agony of a massive CI/CD build process failing at 99% and having to start all over again from zero.
It's the worst.
It is. If your agent spends 20 minutes successfully fetching data, formatting it, and setting up the API, but then it hits a minor syntax error on the final routing step.
And its reaction is to wipe the entire project and start fetching the data all over again.
Right. You do not have a useful agent at that point. You have a massively expensive token-burning machine.
Yeah, state preservation is literally the only way to make an agent economically viable and functionally useful. You cannot throw away good work.
So how does the architecture handle that?
Well, when the critic agent flags a failure, the orchestrator needs to cache the valid steps. It needs to isolate the specific node that failed, query the LLM to patch just that node using the error context, and then resume the broader execution graph.
Okay, you just mentioned the execution graph, which is actually the perfect bridge to how we prevent these massive cascading failures from happening in the first place.
Oh, definitely.
Because to stop the agent from constantly hitting walls and throwing out good code, it needs to understand how its subtasks actually relate to one another before it writes a single line. It needs dependency management.
Right. If task decomposition is the act of breaking a massive boulder into smaller rocks, dependency management is the architectural blueprint for how those rocks actually stack together to form a wall.
That's a great analogy.
Thanks. It solves two existential problems for autonomous agents: correctness and performance.
Correctness makes sense. It ensures sequential integrity, right? Like, the agent can't query a database table before the subtask to create that table has been successfully executed.
Exactly, that's straightforward. But performance is where the architecture gets genuinely exciting.
It is a parallelization.
Yes. Dependency tracking is the mechanism that unlocks parallelization. By mapping out a directed acyclic graph, a DAG, of the subtasks, the agent's orchestrator can identify exactly which processes can run concurrently.
Let's break down how that actually happens under the hood, because, again, an LLM's just a text predictor. It's not sitting there drawing a flowchart on a whiteboard.
Right.
How do you force a language model to output a functional DAG that a Python orchestrator can actually use?
You rely on strict structured outputs. You do not ask the LLM to simply describe the dependencies in natural language. That will fail.
So what do you do?
You use a system prompt with constrained decoding to force the LLM to output a strict JSON array.
Okay, structured data.
Right.
Yeah.
Every subtask in that JSON object must have a unique task ID, a description, and crucially, a dependency array that contains the IDs of prerequisite tasks.
Got it. And then your deterministic Python backend parses that JSON.
Exactly. And if it sees that task C depends on task A, but task B has an empty dependency array, the Python orchestrator, not the LLM, the orchestrator spins up a secondary thread to execute task B simultaneously.
Wow. So you are taking your execution time and slicing it in half while optimizing your API calls
It is beautiful when it works.
when it works. But there is a massive trap here, isn't there? The silent killer of parallel execution.
Oh, implicit dependencies.
Yes.
Yes.
Let me give you a concrete code example for the listeners. So you're looking at the agent's JSON output, and you see module A and module B. They have no explicit link. They don't import each other in the code base.
Okay.
So the Python orchestrator fires them both off simultaneously on different threads. But what the LLM failed to realize is that module B implicitly relies on a specific version of a global logging library that module A installs during its setup phase.
And you have just introduced a race condition into your agent's workflow.
Exactly. If module B finishes executing before module A has installed that global library, module B fails. It crashes because the underlying environment wasn't prepped.
Right, but nowhere in the prompt and nowhere in the code syntax did it explicitly state that module B requires module A.
So how do you catch that?
It's hard. Implicit dependencies are notoriously difficult for language models to catch because they require a deep contextual understanding of the entire execution environment, not just the isolated code blocks.
So what's the solution? Do you force the agent to, review the package.json or the requirements.txt before it builds the DAG?
State awareness is really the only mitigation. You have to provide the LLM with the global environment state during the planning phase.
Before it writes the JSON.
Right. It has to know the current dependencies, the existing architecture, and the system variables before it outputs that JSON array. If it lacks that global context, it will always assume a sterile, isolated environment for every task, which leads directly to those race conditions.
Okay, so bringing this all together, what does this actually mean for you, this software engineer trying to build this? It means that architecting an autonomous AI agent is not about prompt engineering.
No, not at all.
Prompting is just the interface.
Yeah.
What you are actually building is a highly complex project management system.
Exactly.
You are engineering task decomposition algorithms, JSON-enforced dependency graphs, adversarial evaluation layers to pipe standard errors back into critic models.
And state preservation caches to keep your API costs from just spiraling out of control.
Right.
The LLM is really just the reasoning engine at the center. The scaffolding you build around it, the DAG parsers, the execution loops, the state observers. That is what transforms a text predictor into a functional software agent.
You're engineering resilience.
Yes, you are building systems that anticipate friction, recognize failure, and adapt without losing their place in the broader architectural vision.
Basically, you're building the guardrails to keep the genius model from walking off a cliff.
Precisely.
But as we wrap up this look into how agents plan and execute, we need to leave you with one final, really critical missing piece.
Yeah, this is important.
We've talked about breaking monolithic tasks down. We've talked about parallelizing execution, surviving errors, graphing dependencies. But honestly, none of that matters. Absolutely none of it if the system cannot remember what it did yesterday.
Memory architecture.
Yes, think about it. An agent that can generate a flawless DAG and recover from a syntax error, but forget its entire context between sessions, is completely useless.
It's like a brilliant project manager who wakes up every single morning with total amnesia.
Exactly.
Yeah.
You could have the most beautifully optimized parallel execution loop in the world, but if the agent doesn't remember the client's core requirements from yesterday's session, you're back to zero.
You really are.
So as you close out your IDE tonight, think about this. How do you engineer persistent semantic memory? How do you ensure that your perfectly planned agent actually retains its architectural context over days, weeks, and months of execution?
It's a tough problem.
It is. Think about how you would build that state retention layer. We will see you on the next deep dive.